You said mod z greater than 0.3, and the unit circle is probably somewhere over here. So the unit circle is a part of the ROC, so it's stable. But unlike this guy, the ROC begins at 4 and it's going outwards again, and the unit circle is going to be somewhere here, so it's unstable. Again, the same thing that we saw earlier. Back to the problem. The first part is finding just the h of z and giving the region of convergence. So this is the h of z. Just this is correct. And what about the ROC? You have two separate ROCs from the two terms. So what do? You take the intersection. And so this guy says more than 0.3. This one says more than 4. The intersection is going to be just that. So that was A. Then you're asked to find the poles of h of z. So just simply equate the denominators to 0 and solve for z. So this would probably give you, z equals 0.3, and this is going to give you z equals 4. Right, that's when the denominators turn to 0 and h of z becomes infinite. So these are the poles. Then change h of n to make it stable without changing h of z. And I think we just did this on Monday. So change h of n to make it stable without changing ROC. So this was our like the unstable term, right? This guy or this guy, and this is stable, so we don't need to change this. So when I'm writing h of n, so you write the stable terms as they were. So it was 0.3 to the n u of n, so it stays unchanged here. But the other term, which was 4 to the n u of n, you remember, if something gives you, if a to the n u of n gives you 1 over 1 minus a z inverse, you have another sequence, negative a to the n u of minus n minus 1, that gives you the same z transform. And the difference is the ROC. This is like a causal sequence. The ROC is outside of a circle. This is anti-causal because of the negative n, and the ROC is inside of a circle. And for exponential sequences like this, if they're tending to be unstable in one direction, they will be stable in the other. So if you're given the causal version which is unstable, you can simply write the anti-causal version here, which will automatically be stable, and it will also have the same z transform, h of z. If you're given this guy and this is unstable, then you just write the causal version of it. So for this guy, what it's going to be, you have a negative sign, then a to the n, which is again 4 to the n u of negative n negative 1. So this term here, now it's both of them are stable. This was stable as it is, and this is like a decaying exponent in negative time.
Doesn't that change the ROC?
Yeah, so the problem said just don't change h of z, but okay, maybe you are allowed to change the ROC. Yeah. So we're gonna change the ROC again. In real life, you can just do something like this. This is just an example and just demonstrating the theoretical concepts. You're just flipping the signal and calling it stable. then give the ROC of the answer from part B. What's the new ROC? So what was the ROC for this term? You go back to your answer from part A. You had the ROC z greater than 0.3, so it's still going to be the same here for this term. I mean, we didn't change anything here. It's still the same, z greater 0.3 to the nu of n. The ROC is unchanged, but for this guy we changed the ROC. So if the original ROC was this, we changed it to that. So here the original ROC was z greater than 4, so the new ROC has to be z less than 4. That. So what is the ROC of the whole sequence? It should be the intersection, right? And this looks like a ring, right? It's going to be mod z greater than 0.3 less than 4, and you just have to write this, but it's going to be something like this. So that's your new stable ROC, and you notice that it includes the unit circle, right? It's in here somewhere in the middle. So this is stable again. No, this was D. This was C. Okay, messed up the numbers. Yeah, this was, the whole thing was C. This was D, and E is asking for recursive difference equations for the filter. Huh? On the figure? Where? Oh yeah, that should have been 4. I'm sorry. Yeah, that's a 4. And so recursive difference equations for a filter. You remember for any h of z, like 1 minus 2 z inverse. I mean, you just cross multiply. You write this guy as y of c over x of z, then you cross multiply and you take the inverse z transform. So in this case, the h of z, it's not a single term, it's a sum of 2. So you had 1 over 1 minus 0.3 z inverse, and you had 1 over 1 minus 4 z inverse. So and again, the question mentions that you're looking for the parallel form, so it means that you have to treat these as two systems connected in parallel, something like this. So the input coming in is x, the output coming out is y. And for these individual blocks, the input is still x for both of them, but the output is not equal to y. It's going to be different, and you can call this y1, you can call this y2. So there will be one difference equation relating y1 and x, there will be one difference equation relating y2 and x, and your output y is just their sum. So the answer is made up of 3 equations, and again, this might be your h1 of z, this might be your h2 of z. So another thing, the question specifically asks you to make sure the equations are stable. So we'll consider that later once we finish writing them. But for the first system, you have the h1 of z is y1 of z over x of z, Like that's how you define the transfer function, the output transfer function over the input transfer function. And you equate it to 1 over 1 minus 0.3 z inverse. When you cross multiply, you end up with y1 of z is minus 0.3 z inverse y1 of z equals x of z. And you can write the inverse z transform now. And again, once you're fluid with all of this, you won't have to like go through all of this. You can directly see that the difference equation is y1 of n plus 0. Okay, I'm just gonna write this down. So it's 0.3, and then y1 of z would have given us y1 of n, but because of the z inverse, you have y1 of n minus 1 equals, this would give us just x of n. So the final difference equation is, so whenever you write a difference equation, you're evaluating y at the current time at n, and you're gonna express that in terms of either the future values of y or the past values of y based on what you need. So in this problem, like the stable version that we came up with, it was causal, right? It's a causal system. We can see that it has a u of n, it's causal. So we have to write the causal difference equation, which means y of n in terms of y n minus 1s. So it will be 0.3 y 1 of n minus 1 plus x of n. So this is clear, right, everyone? And then for the second system, h2 of z is 1 over 1 minus 4z inverse, which is y2 of z, because the output of the second system was y2, not y or y1. It was y2 over x of z. Again, you cross multiply and then you take the inverse z transform. I'm just gonna write the equation that comes out. You get y2 of n minus 4 times y2 of n minus 1 equals x of n. Now again, you could always write y2 of n in terms of, like this, but this is wrong for this particular question. It is asking for the stable version. The stable version that we came up with was anti-causal. This is, you have a u of negative n, so it's so you have to come up with the anti-causal version of this equation. And how would you do that? You look for the term of y with the maximum delay. So this is the term with the most shift, like most negative shift. So I'm going to keep this on one side, and let's say okay, I can say minus 4 y2 n minus 1 is x of n minus y2 of n, which gives me y2 of n minus 1 is 1/4 y2 of n minus 1/4 x of n. And finally, a proper difference equation is, so this is kind of, it's expressing y of n minus 1 in terms of y n, so it is anti-causal as it is, but you have to express